So now we see some examples for the synthesis of multiple substituted benzenes. And you can see in the first row here, we start with methylbenzene. That's also called toluene, that you've probably also heard already. And we want to do a nitration reaction. So we are using our nitric acid together with sulfuric acid. We are joining our nitronium cation here that acts as an electrophile. And now we see this product distribution here. So we are seeing roughly 60% of the ortho nitro toluene. Then we see roughly 40% in the para position, so the para nitro toluene, and we only see 5% of the nitro group ending up in the meta position. And this is something that we can directly explain with the activating influence. So the methyl group here in this case acts as a plus I substituent, so it pushes electron density into the ring. It's slightly activating, but it also, and more importantly, directs the subsequent electrophilic substitution reaction into the ortho and para position. And that's what we exactly see. 60% happens here in the ortho position and 40% happens in the para position, and these 5% in the meta position are neglectable. And you see that's exactly what we would expect from the resonance structures. 2 position and 4 position are activated. Something that you of course need to consider in this way is that you if you already have a strongly deactivated aromatic core, for example like here this nitrobenzene here, then if you want to add something to this core, then the reactions can sometimes not occur, and this is a problem. For example, if you already have something that needs a lot of, or a strongly, or at least a normal benzene core to proceed. Examples, for example, could be these Friedelcrafts, acylation, and acylation that we've discussed. They already need a lot of electron density, and if a nitro group is already present, that basically pulls out a lot of electron density, then these agents or reagents are not able to attack this electron density here anymore, so we do not observe any reaction. Something else that can happen is, of course, if you want to do a Friedelcrafts acylation at, for example, this aniline molecule here with the amino group, you would say, oh, nice, the amino group is activating group, so the reaction should proceed as I would expect. But the problem is that your Lewis acid, here the aluminium trichloride, gets deactivated by coordinating towards the amino group. So that's actually the complex that you form. And if you do not put like an excess of aluminum chloride, you don't get any reaction at all. And even if you put like a strong, large excess of aluminum chloride, this doesn't help because like your Lewis acid is pulling away the electron density of the amino group that was previously activating your benzene core. And this is then this amino group, or this coordinated amino group, then acts as a deactivating molecule. So this is something that then also shows no reaction inside this Friedelcrafts acylation and acylations. Another trick that you can do here is, for example, the shown in the synthesis of TNT, trinitrotoluene, and this is something that you can nicely do in the lab. The first step is, of course, to prepare this nitration reagent here with nitric acid and sulfuric acid together on toluene. What we've seen before is that you would get the ortho and preferably the ortho and the para-substituted product here. And here is shown as an example the para-substituted product. And this reaction proceeds at room temperature. If you now want to introduce another nitro group, your core is somewhat activated from your still present methyl group, but you already have a strongly deactivating nitro group. So you need to crank up the temperature to actually get the second nitration going. So in this case, in ortho position to the methyl group and in meta position to the previously introduced nitro group. So you always need to also take into consideration the interplay between these, for example, 2 functional groups that are present here. And because you want to go to trinitrotoluene, so TNT, you need to introduce a third nitro group. And in this case, you need to heat up even more, so to 110 degrees. That's somewhat close to the boiling point of toluene already. And you also need to change your activating agent a bit. So you need to go from sulfuric acid to sulfuric acid plus the sulfur trioxide, and this acts as an even stronger activating agent. And then you can also push the next or the third and final nitro group onto your already substituted benzene molecule, and then you end up with this trinitrotoluene. And this is something where the previously introduced nitro groups act as deactivating towards your desired subsequent reaction steps. So you need to take this into consideration.